engines and energy systems. He is a specialist in the field of spark ignition combustion, pressure charging systems, alcohol fuel, and engine fuel interactions. He has nearly 30 years of experience in the field, and by the looks of it has published many papers and books, or book chapters. He spent over 21 years working in Lotus Engineering, where he was the chief engineer for powertrain research. Some of his main areas of specialization are in renewable energy and its application to the transportation sector, with a particular emphasis on the use of and possibilities offered by alcohol fuels. One of the more interesting utilizations of that seems like the performance development of a methanol burning IndyCar engine. As well as being at Lotus, he has also worked at Norton Motorcycles, Cosworth Racing, and Jaguar Land Rover. His talk today is titled Some Novel Engine Technologies for Hybrid Vehicles, Leveraging Electrification for Improved Thermal Power System Attributes. So, thank you, Jamie.
Thank you very much, Graham. Yeah, I guess after that introduction of the methanol stuff, I usually start these talks by just walking up here and saying, hello, my name's Jamie Turner, I'm an alcoholic. And then I go on and talk about the wonders and glories of methanol and ethanol. But here I'm talking about something else which I'm very, very keen on, actually, and that is I'm actually very keen on electrification. And that's because it's a great opportunity for us as engine people. We've got really power-dense machines coming along which will allow us to do some stuff, and I'll talk about some of those things. We've got the ability to operate our engines in very specific areas. We've got the ability to look at engine concepts which maybe have been laid dormant for a bit. And this is all great. You know, it opens the door to more things that we can study. And as an academic, of course, that's absolutely great for me because I don't have to put anything into production. But, you know, it's a fantastic area to be in. And I have the very good fortune to teach our brightest students about internal combustion engine technology. And obviously they're brightest students because they've chosen to do internal combustion engine technology. But I tell them, you know, we can't tell you everything. The engines are going to be around for a very long time. There will be more electrification. But I also tell them, my honest belief is, we've heard the phrase, people say there's no silver bullet. And I think the problem is that the internal combustion engine has been the silver bullet. And almost by definition, you cannot replace a silver bullet with only one thing. So we will see electrification, but I think we will also see much more advanced internal combustion engines running alongside. And I think that's the thing we have to prepare ourselves for. Having said all of that, I do tell them that the battery and the fuel cell are both significantly older than the internal combustion engine. And so if you want to work with the most modern technology, work with engines. And that doesn't go down too well with some of them, but it is the truth. Now, just before I start, because it was said yesterday about engines cleaning the air, maybe they do, maybe they don't. But I've got a bit of, it's just a bit of information from the local newspaper where I live, a small city called Norwich in England. And they banned cars from a certain street in Norwich where they got a real problem with NOx and particulates. And the other day there was a piece in the newspaper saying that since they banned cars in that particular street, the NOx levels have gone up, which is quite interesting. I wouldn't like to be able to point to any real scientific evidence on the subject, but there's a lot of local councillors out there scratching their heads, wondering why. And there's the engineers out there pointing to the fact that they've got really old buses running up and down that street and no light-duty vehicles. Anyway, there we go. I will now start my talk. There's been absolutely no collusion between myself and Fabian Renault. But you will see certain things that in my presentation, which he's already said, but I talk about several different things here, and I'll start with some sensible stuff, and then we'll suspend some disbelief as we go through it. And then I'll finish up with the project that we're working on at the moment. So, some novel engine technologies for hybrid vehicles. So I'm very much leaning on electrification here. How are we going to leverage it to improve thermal power system attributes? And I just want to give an acknowledgement to a couple of my colleagues who helped me a lot in some of the stuff that I'll be talking about here. Dr. Giovanni Ferraro, who's here with me, and also Matthew Turner. So I do want to acknowledge their input. So, electrification of the boosting system, and this will come as no real knowledge to anybody. I don't think this has been one of the things in engines we've latched onto first. electrifying the boosting system with e-superchargers, etc. We did some work on an engine called Ultra Boost, which I'll talk about here, with a novel electromechanical supercharger called Supergen, which is out there at the moment. It differs quite a bit from a normal e-booster, if we're allowed to use that phrase. I think it's actually been trademarked, but anyway, I'll use the phrase e-booster, insofar as it uses a mechanical input as well as an electric one. So that means that it can transmit much more power to the centrifugal supercharger, and therefore accelerate it faster through a greater pressure ratio. And so we tested it on Ultra Boost, and obviously with increased electrification on the vehicle, mild hybridization, we've got increased electrical power for support systems. So e-supercharging is one of those support systems. We started doing e-boosters with 12 volts, and they sort of worked. They did do quite a few good things on cars back in about 2000, but really it's very difficult. You've got about a kilowatt of power that you could use at that point. So it lay dormant for quite a while, and it really took the onset 48 volts and mild hybrids before that sort of e-booster could start to yield decent amounts of power, up to about 7 kilowatts, I guess. But some of these devices, Supergen specifically, can actually perform more than one function. It can perform a boosting function, it can also do stop-start and mild hybrid, and that's because it effectively replaces the alternator in the run. So we tested this on Ultra Boost. And Ultra Boost was a 2-litre, heavily downsized demonstrator engine, a 2-litre engine that could generate 400 horsepower, 500 newton meters, etc. And although it was a while ago now, it was designed to effectively replicate the torque curve of a 5-litre V8 engine. So it represented about 60% downsizing. And on the next few slides, I'll show some of the results and how it happened. But we tested this just in a 12-volt form, not the 48-volt form. So, Supergen is effectively created by Integral Powertrain. It's a variable speed centrifugal compressor. It uses an electric input to modify in an integrator, effectively an epicyclic gearbox, to modify the speed of the centrifugal compressor. And because it's an integrator, a lot of the power comes in off the belt, and you use the electric power essentially to change the speed of the centrifugal compressor. It fits where the alternator goes in the front-end accessory drive, and it functions as the alternator as well, and as a motor generator. So Ultra Boost itself had a 2-stage boosting system. So it had a turbocharger as the low-pressure stage. Turbocharger went through a charge cooler, then it went through a supercharger, which could be declutched, the normal supercharger, the R410 Eaton, and then it went through another charge cooler after that. So what we did was essentially replace the R410 in that run with Supergen. And at steady state, this is what we got. So this is all charge sustaining. What we've got here is the target. So the target line's in black. The thing that the R410 that we originally ran gave the steady state torque curve shown in the blue there. What you can see there is that was the only real significant miss that we had within the project. The low speed torque, the R410 just could not provide enough boost with the turbocharger in series to be able to meet the low speed torque target there, which was 400 newton meters at 1000 RPM, which I think is about 26 bar at 1000 RPM. So we put Supergen on, and that made things much, much better. We almost made the low speed torque target using Supergen. And I say again, this was charge sustained, so the power was coming all from the crankshaft. There was no extra power that we weren't accounting for coming from a battery or anything like that. So that was a very good start to it. We managed to get very much nearer to where we wanted to be at the original set out of the project. But also, the fuel economy was largely equivalent, and we've always thought we had the potential to improve. So here you can see in the red line, the original R410 line, if you like, with the yellow line. When we ran it unoptimized, we got slightly worse. But for one of the points there, because we did a bit more work. We found we could get better fuel economy there at 1500 RPM. We didn't quite achieve the same at 1000 RPM, but we had other stuff that we could have done. We didn't change the cam timing, we didn't change any of the other parameters essentially. So we thought that we could probably get down to the same fuel economy or slightly better charge sustain. Obviously, when you put it on a vehicle, you can then recuperate some power, and that was about 20 kilowatts of hybrid power it could have done. But also, the time to torque was massively improved, the 10 to 90. We had about 68% reduction at the matched full load condition, if you like. So it came down from 2.5 seconds with the normal R410 at 1000 RPM, down to 0.8 of a second using superjet. So that's really a very, very big improvement. And if it ever made it into a vehicle, it would have obviously made a huge difference to the drivability of the vehicle. And you can see the time to torque there, so about 68% reduction. But of course, it's just one example of the novel use of electrification in conventional four-stroke engines. But with all this electric power that we're going to have in the future, who says that we have to stay with conventional four-stroke engines? Yes, I know mainly the accountants that say that we have to stay with conventional four-stroke engines, but there may be a better way. So the rest of this talk really will talk about perhaps electrification will free up some other forms of engine technology that we might be free to look at. So, the opposed piston engine as an advanced hybrid engine. And most of these presentations, I can't resist putting mad old engines in. I know it's a light duty session. This is a Junkers engine. You can see here it's got 24 cylinders and 48 pistons. Really quite an achievement mechanically. It's a opposed piston engine. It's got 4 crankshafts, 4 banks. Hell of an achievement from a mechanical engineering point of view. I'm not going to suggest that we start putting those into hatchbacks, but it would be nice. So those people who know me would have been disappointed had I started talking about the opposed piston engine and had not put a picture of a Deltic in. So there's a Deltic, 3 banks, 3 crankshafts, but the pure form, obviously, as we've seen in Fabienne's presentation, really on the cylinder basis, it's about 2 pistons moving in the same cylinder in opposite directions, slightly out of phase. And that's because it gives us asymmetric timing, which is extremely good for trapping, and gives us very, very good balance, as Fabienne said. And the configuration gives you, essentially, it gives you uniflow scavenging, which is extremely good for a 2-stroke engine. Now, the crankshaft phasing is really good because it gives us the asymmetric timing. The intake closes after the exhaust, so you can slightly supercharge the cylinder if you want to. But the timing also affects compression ratio for a given set of components, and I'll come back to that in a minute. So the characteristics of the cylinder, if you like, are there's a ring of, how we've drawn it here, ring of intake ports at the base, you've got a ring of exhaust ports at the top. All the ports are piston controlled, so we don't have any valve train dynamics, kinematics to worry about. And the exhaust lead itself allows for cycle optimization. Now, as you look at these things, you might think that the primary disadvantage is that the fuel has to be introduced from the side of the cylinder. That may not be an advantage, maybe it is. But what we can say is any combustion system which allows you to introduce the fuel significantly before you want to burn it might be really good. So GCI is perhaps a bit of an obvious thing to apply in an engine like this. Obviously, KTs have their GCI demonstrator engine running at the moment. So this slide actually comes from a paper that I did at Fuels and Lubes. In that paper, I compared 6 different scavenging systems for 2-stroke engines. Many conventional forms of engine, they all had asymmetric timing one way or another. They all had the same sweat volume, they all had the same geometric compression ratio. They had as many things matched as we felt we could match, the same targets. We did allow the bore-to-stroke ratio to vary because that has a big effect on scavenging when some of them had poppet valves, some of them had ports, one of them was loop scavenged, etc. And what we found from that was that the opposed piston engine was quite clearly the best of all the systems that were tested. It was about 8% better than any of the others. The rest were really quite close together. And so that's sort of fired up an interest in me. I was always interested in these engines before, but at that point I thought we'd done a sufficiently fundamental piece of work and really was persuaded that there was something in the opposed piston engine. So that makes you think about things. We know that it has advantages anyway over 2- and 4-stroke engines due to reduced heat rejection, potentially improved mechanical efficiency because it is a 2-stroke engine after all. And we found that the opposed piston engine, you can configure it to have a really good ratio of expansion ratio to compression ratio. In fact, in terms of trapped values, we got it to 1:1. So it's nearly a millicycle engine, nearly a milli, insofar as the expansion ratio was nearly bigger than the compression ratio. Now that's something you don't usually associate with 2-stroke engines, the ability to have an expansion ratio that's greater than the compression ratio. And that was really one of the really good things about doing the fundamental study. It allowed you to look at things like that. But also we found that the ratio of exhaust power to the total input fuel power is very high for the opposed piston engine. That's because it rejects much less of the energy as heat. And because of that, it means that turbo compounding would theoretically be very beneficial. We also know that full-range, low-temperature combustion systems have been found to be possible in 2-stroke engine. We had an engine with a wide-range variable compression system that was tested. It was loop scavenged, but we managed to crank start it on gasoline and diesel. We could run it throughout its operating range by changing the compression ratio, always in HCCI. I used to think that was a really impressive claim until I saw Mark Selnow's presentation earlier on today. I now feel a bit chastened to be saying this now, but what I would say was we could run this thing on gasoline, diesel, and E85. And essentially that was enabled by variable compression ratio. So for me, VCR, particularly in 2-stroke engine, is a really desirable thing to have. And of course, in the opposed piston engine, we now know already that KT's Aramco have shown GCI is possible across the full engine map. So this might be the place where low temperature combustion systems finally come to some form of large fruition, shall we say. So that was the paper number that we did the fundamental comparison in. It was essentially funded by Aramco, very grateful to them for doing that. But it did lead on to various other thoughts for the opposed piston engine. So conventional hybridization of the opposed piston engine might look something like this. So you've got your two intake and exhaust cranks, top and bottom respectively, on that drawing. We've got the turbocharger, we've got supercharger, we've got 2 charge air coolers, we've got an EGR cooler, catalyst, etc. But conventional hybridization, you would put the electric machine probably there on the output from the exhaust crankshaft. And the reason you would do that is that a peculiarity of the engine when it has exhaust lead is that the exhaust crankshaft produces more power than the intake crankshaft, which I'm not going to go into the reason for that in any great detail here, but it is quite a peculiarity, easy to see when you see it written out as a cycle. So that's how you might hybridize a normal opposed piston engine, and without the hybrid system, that I think is essentially what the configuration of the air path of the KT's engine is. So if we're going to improve the opposed piston 2-stroke, you probably want to look at technologies in the following areas. So maximize use of hybridization. We want to really embrace this opportunity afforded to us by electrification in the vehicle. We want to be able to control combustion much more tightly, and I'd suggest that what we really want there is wide range variable compression ratio. We'd like improved mechanical efficiency, because we always like that. We don't want to throw heat away as friction. And we'd like to improve waste heat recovery while we're about it. So if you could find some means of doing that, you'd feel quite pleased with yourself. Now, variable compression ratio for the opposed piston 2-stroke engine. So in theory, the opposed piston 2-stroke engine can be relatively easily given variable compression by varying the exhaust piston lead dynamically. And we know that VCR is a strong lever on low temperature combustion. We did look at some of this in the paper that was published in January. While keeping all of the ports, we didn't change anything else, we just changed the phase. And it showed very little change in indicated specific fuel consumption as the lead was varied across quite a wide range. So we think that's worthy of some consideration with respect to combustion control. So the diagram there, the indicated specific fuel consumption chart at the top, the vertical blue line is what the optimized lead was. So we varied the lead in both directions, and you can see that the specific fuel consumption indicated is pretty flat there. That's good, it's flat, so that means that we can vary the compression to control the time of combustion, but we won't have a disastrous effect on specific fuel consumption. That's the takeaway from that. Value of turbo compounding. So, the bars here are from an earlier paper, but essentially they're different types of scavenging system for a two-stroke engine. I won't go into too much detail. That is the classic Detroit diesel uniflow scavenged arrangement. That one on the end, for anyone who's heard of crazy old aircraft engines, that is a sleeve valve two-stroke uniflow engine. We investigated it as part of this fundamental study. But what you can see is the opposed piston engine here has the lowest power or fuel input rate to make the target indicated power output. And if you look at the ratio of the bars, the blue bar there is about 35% of the total fuel input energy. So if we could recover 20% of that, theoretically we might look to be able to improve the indicated thermal efficiency by 7 percentage points if we could recover that. So I must say that that chart is a breakdown of indicated power. It's not an efficiency comparison. You have to go in and read the papers to understand what we're getting at there. But the heights of the bars are important. And as I say there, the opposed piston two-stroke engine requires the lowest indicated power to achieve the target, the lowest fuel power to achieve the indicated power that we're after. And the low scavenging work of the opposed piston engine, which is afforded by the fact that it uses rings of ports, top and bottom, so the flow areas are very large. That means that the work requirement to scavenge the engine is very low. And so if you had a turbo compounder on the engine, you would expect to be able to recover a lot of energy because the work ratio of the turbo compounder will be high. What you can get out of the turbine will be much greater than what the compressor requires to be able to push air through the engine. And so that obviously further improves the situation. So if you put all these things together, you might wind up with something that looks a bit like this. So I christened this isotope because there's nothing in this world quite as satisfying as a really well-constructed, contrived acronym. And the acronym stands for Integrated System to Optimize the Thermodynamics of Opposed Piston Engines. That took quite a long time to think of, but I was determined to have something that I could remember. So here what we've done is we've replaced the gear linkage between the two crankshafts with electric machines. So this is what Fabian was talking about earlier on. We've now got an electric machine on a turbo compounder, and they're all going to the hybrid control system, this magic box that I don't know anything about, but I'll put it down there, and there's obviously a battery. So this, you might think of this as being a way of really going to town, integrating the systems together. So you could have a series configuration with this, but also you could have a parallel configuration as well, if you wanted to. The maximum compression ratio is not limited by valve cutouts, as it is in a four-stroke engine. So two-stroke engine, no valves, you just bring the pistons closer and closer together. But you can eliminate piston-to-piston clash at the design level. So if you lose control of the electric motors, you won't crash the pistons into each other, as long as there's a slight gap between them when they're both at their own top dead center. So that would be the design level requirement for that. So this would be worthy of greater investigation. And as I say, there wasn't any collusion with Fabian's presentation. He's actually going out and doing it, which is fantastic. So there are other advantages if you electrify the crankshaft linkage. It gives you the variable compression ratio thing, but it will give you lower friction because you've now lost the gears. You've got lower engine cost. Obviously you've got to have the electric machines. You've got improved assembly. You've not got the challenge of machining tolerances for all the gear stacks, etc. You've got improved NVH, another thing Fabian mentioned, and obviously you've got reduced engine mass as well. So quite an interesting idea, I think. However, it's not a new idea. I won't tell you which organisation that was that had that patent, but I'm sure some of you in the room could probably guess. There's a patent from 2007 looking at applying electric or indeed covered hydraulic machines as well as a phase control mechanism for an opposed piston engine. Okay, so that is looking at the opposed piston engine as an advanced hybrid engine. So some conclusions one might reach is if you introduce significant electrification to the idea because of full hybrid operation in the vehicle, you'd have an opportunity to improve efficiency. I think one of the first things you try and do is remove the phase and gears and replace them with electric motors to give yourself VCR for combustion control, reduce mass of the engine and the manufacturing cost, and improve MPH. You can apply that to either series or parallel operation, and I think if you could add electrical turbo compounding, you'd have even more potential because it would simplify the boosting system. And we're studying that at the moment, geometrically and then in 1D, as a continuation to the two-stroke work we started with Aramco. So that's very interesting. We'll see where that takes us. As I say, it's something that's been at the back of my mind for quite some time. Now I've got an excuse to go and look at it properly. So that's the opposed piston engine. Rest of this talk, I'll now talk about really highly efficient engines. I'm going to talk about Wankel engines as a means of improving fuel economy. So the reason I put this up, Mercedes-Benz 4-rotor engine, is because it has direct injection during the low pressure part of the cycle. During combustion, the injector is completely cut from the combustion chamber with a Wankel engine, and it's one of the opportunities that you've got, the fact that the cycle is laid out in one direction all the way around it. So that's something we're going to be looking at when I come to talk about it. But also, this is a great, wonderful engine. In fact, I believe it's the only engine in the world that was ever fitted with 2 throttle pedals. And I won't go into any reason for that other than to say that it had such incredibly low inertia that if you blipped the engine with the main throttle pedal, you'd send it straight round to the red line. So there was a special throttle that you used for heeling and towing. I know the young people in the room have just driven automatic cars will not understand what heeling and towing is, but that is a very important part of learning to drive, learning how to heel and tow. Anyway, I'll carry on, but the reason I mention that is the low inertia thing. So we'll come back to that in a minute. So range extenders for plug-in hybrids. Obviously, several organisations have shown this. Chemical energy converters, Lotus, Marla, Tata. We're looking at reciprocating 4-strokes, AVL, FEV, AIE. It's a company I'll come back to in a minute. Looking at the Wankel rotary 4-stroke. Other organisations obviously have commercialised these things. BMW and Chevrolet, who had a direct power transmission when they could. And Mazda, interestingly, has just announced a vertically mounted Wankel engine for range extender use. And that will be sold to third parties. I believe Toyota are going to buy it. That's an engine that was done partly at the University of Bath with Tata, looking at using Tata Nano engine as a range extender. Also, people have looked at some really crazy stuff. People are looking at gas turbines. Delta Motorsport, this thing called MITR, Micro Turbine Range Extender. We tested that at University of Bath. It's just an excuse to put a picture in with a rare pink glowing combustion chamber that we tested on our turbocharger rig. Interesting piece of equipment, quite light, but there are also solutions using fuel cells, we know about that. And now there are some studies showing us what the benefit is in terms of mass with these things if you have a light range extender. But the trade-off still demands that the thermal efficiency of the energy converter be good enough. And we're involved in a UK Advanced Propulsion Centre funded project to study novel Wankel engines for range extender use. I would highlight that phrase. For range extender use, it needs to be good enough. It does not need to be absolutely world-leading, because it's hardly ever on. It's about the trade-off between the mass on the vehicle level and the efficiency of the engine. So this project is the ADAPT project with all those partners there. AIE is effectively the engine manufacturer. So the Wankel engine is a range extender. It's got some interesting characteristics which might make it attractive for use as a range extender, and those include low installed mass, the obvious one, low inertia, which is important for a range extender because of when it starts up and shuts down. The refinement of that process is really important. It obviously has excellent balance, perfect balance, and it has compact size. However, the disadvantages, which we all know, include emissions, fuel consumption, and durability. And the first two of those are the things that we're looking at the university. But before I say that, obviously the Wankel engine is not normally associated with high fuel efficiency. We all know that. That's the reason really why it died out before in the 70s, 80s. But Mazda actually did beat all competition with it on just this metric. At the Le Mans 24 Hours, the last year of the fuel consumption formula, heavy irony, they beat all the four-stroke engines and won it outright with a Wankel engine. And that tells you everything you need to know. That is that the Wankel engine has pretty good fuel economy as long as you run it at full load. If you do something stupid like run it at part load, it all falls apart on the fuel economy level. So that is the Mazda that won, and I had the good fortune to hear that race at Silverstone. And I tell my students, go away and Google this car and listen to it, because the sound that the engine makes is, in my opinion, the best sound that the human race has ever made. It is stupendously good, and I urge you all to go straight away to YouTube and Google Mazda 787. However, going off topic, part load fuel economy in the Wankel is frankly appalling. It's poor because you've got a really bad surface area to volume ratio. The combustion phasing limitation is there because the combustion chamber is continuously moving. You've got charge leakage across the sealing grid, both from the chamber to the chamber and from the side seals to the core. That's Mazda's twin plug arrangement that they came to with differentially fired plugs to try and get combustion better, because as the trailing edge goes past the minor axis, it always tends to quench the mixture that's left there. That is the sealing rotor, the sealing grid of an air-cooled rotor, and I'll come back to that later on. So obviously pretty complicated compared to set piston rings. However, as I said, the Wankel full-load fuel consumption is broadly comparable to a four-stroke engine. So we went away and did some literature search for Mazda Wankel engines, essentially, and we think full-load BSFC is not too bad when you compare it to simple reciprocating four-stroke engines. All of those are port fuel injection engines. So the best one there is down at about 280. That's actually the race engine, 787. And the reason is for that is that as you go up in speed, there's a declining proportion of charge and heat losses with load as well, and it has extremely low friction, and that makes downsizing less attractive in the Wankel engine. All of those are turbocharged, all of those are naturally aspirated. So that tells you want really to operate the Wankel naturally aspirated. Generally, the best BSFC of NA Wankels has been in the region of about 270 to 280 grams per kilowatt hour. We can't find the full load fuel consumption for the Renesis, they never published it. So we're actually going to go and buy one and test it and get our own data to see whether it really is any better than what they published on the previous engines. So in ADAPT, this is the project, we're testing a 225cc per chamber single rotor engine made by Advanced Innovative Engineering. It's normally used as a UAV engine. It has an air-cooled rotor with a novel rotor cooling system. I'll describe that in a minute. So the engine specifications there, which will mean nothing to anyone, it has a generating radius of 69.5, an eccentricity of 11.7, and a housing width of nearly 52 millimeters. But it has a compression ratio of 9.6, and it weighs about 10.5 kilograms. It makes 27 kilowatts at 9,000 RPM. It's peripherally ported, but that is not such a problem as long as you run it at full load to avoid the part load problems. And we're also testing it with a Wankel geometry compounder, which we call Creve. I draw your attention to that. This is a very small engine making a lot of power. So when I talk about fuel economy later, do remember that. There's a paper on 11th of April at 10:30 that's being done on the range extender versus mass thing. So what contributes to the lower installed mass? Well, you've got the reduced parts count, high power density and perfect balance. Also the low inertia. So starting is less of an NVH issue, and it takes less energy from the battery. Air-cooled rotors have further reduced mass because they don't have the second side and rotor oil seals. They don't have the oil pump and the oil cooler. And they have reduced friction due to all of the above and the elimination of any oil churn in the rotor. I would suggest that Wankels have high reliability because they don't have many parts, but low durability. That's the problem with the Wankel engine. It wears out. Operation of a range extender, we think, will inherently help this. There have been developments for ceramic apex seals, and the engine we've got has ceramic apex seals. According to AIE, the manufacturer, they don't wear out, is what they say. I'll believe it when it happens. But air cooling of the rotor has historically been achieved with induction air cooling, ejector cooling, or the use of a fan. But now we have this thing called sparks. And this is quite interesting because it seals the core of the engine and fans the air around within that sealed core. So the air inside there does the heat exchange through the rotor. So the oil is recirculated. I won't talk too much about the lubrication system, but the oil is recirculated around this thing. And interestingly, the blow by past the side seals pressurizes the core, and that increases the number of molecules that are in there that can participate in the heat exchange. And that actually makes a benefit out of what is usually a significant problem. So the pressure in there can get up to 5 or 6 bar with the air going around and the side seals. It balances across the engine. But it doesn't blow oil out of the engine effectively. So when we mapped the engine, it shows that clearly, because of the shape of the thing, if you just reduce the load, you get much, much worse fuel consumption. It's not well suited to throttled operation. The best BSFC here is about 290 grams per kilowatt hour at relatively high speed and load. And actually, for a 27 kilowatt engine, I think 290 grams per kilowatt hour is not bad as a starting point with poor fuel injection. But we're compounding it. So the Wankel has been compounded in the past, actually built as the Rolls-Royce cottage loaf engine. Now, I don't know if a cottage loaf is a particularly British thing, but a cottage loaf is a type of bread that has one big lot on the bottom and another big lot stuck on the top. That's a cottage loaf. And it's a compound diesel engine, and it looks like this. So you can see why it's called a cottage loaf. It's got one small one on top of one big one. Now, interestingly, Professor Johansson, this is a double compression expansion engine. And it has some quite serious benefits, actually, as in this configuration. This is the earlier way that it was proposed, and the expanders that this is used here is actually what we're testing. But the cottage loaf is quite interesting because it has low transfer losses through the ports. There are no valves, the ports are extremely short, so your heat losses through them are pretty low. So all the rotors in these things are geared in the same direction, and they're all geared at 1-to-1. So those are the transfer ports of the exhaust. This is the cross-section through the engine that we're testing. Both rotors rotate anti-clockwise in this cross-section with 1-to-1 gearing. The engine swept volume is 225 cc and has a compression ratio of 9.6. The expander is 631 cc. Instead of being a 2-to-3 Wankel device, it's a 1-to-2 Wankel device. The 2-to-3 goes around at a ratio of 3-to-1, and the 1-to-2 goes around at a ratio of 1-to-2. So there's all sorts of interesting things going on geometrically inside this thing. But despite the fact that the expansion ratio of the expander is 29.2 geometrically, because of all the porting, the overall system expansion from spark out to exhaust port, if you like, is only 26.2. Because you have to bring in the transfer. So that's the engine, that's the expander. They go around like this. And the expander has a mass of about 8 kilograms. So now we're up to a core engine mass of about 18.5, under 20 kilograms now. Here it is in a vehicle installation, in a pod installation. But the ratio of the expansion ratio to the compression ratio is 3-to-1. Its expansion ratio is 3 times that of its compression ratio. It's not a millicycle engine. It's not even a super millicycle engine. I would suggest that it's actually operating on the Humphrey cycle, which is something that people haven't talked about for many, many years. And I know there are better thermodynamicists in the room than me, so we can have an argument about that in the bar afterwards. So, initial results, we've tested it. Brake torque and BSFC are both improved at full load. At 4,500 RPM, the overall benefit of just slapping the expander on, torque's up 27.3%, the BSFC is down by 11%. down to 271.5 grams per kilowatt hour. Emissions and exhaust O2 concentrations both showed improvements as well. The exhaust temperature was 350 degrees cooler, which is quite important when you think about catalyst durability. We're down about 500 degrees at this point. For context, the Lotus range extender in its first form was 241 to 248, and the Marla, when it published in its first form, was 252 to 272. So we're already down at that level on the first test. So, summary. I think the Wankel engine does possess some desirable attributes with regards to a range extender engine, including balance, mass, inertia, and small package size. On a vehicle level, I suggest even in an NA form, it's already efficient enough to act as a range extender. You can make it much more efficient through the use of a Wankel type expander, which gives you full expansion, essentially. That might remove the need for significant exhaust silencing. We've shown that we can get significant improvements in torque and efficiency. It's already as good as a simple four-stroke, but much lighter. And further work that we're going to look at, we'll look at optimization of the cycle of the engine expander together, gathering full cycle pressure curves, which is not an easy thing in a Wankel when all the cycles dispersed around it. And also we're looking at direct injection. And the reason we're doing that is, as I said earlier, it's because you can position the injector in a low pressure part of the cycle and never cease combustion. So, thank you for listening.
So thank you to Jamie. We ran a little bit over there, and in the interest of keeping on time with the schedule, we'll move on to the next presenter. But I'm sure if you find Jamie later on and give him some alcohol, you might find out about cycles you've never heard of before. So let's thank Jamie once more.